Welcome back, class. This is the third section of Unit 1. Today we are talking about measurement. In the past, chemistry was largely a science of observation. We heard that on the first day in the first video. It's a science of observation. People notice that changes sometimes occur when you combine two different things. Maybe it was fire, maybe things turned a little colder, maybe it felt hotter. This is a specific type of data. Data that is based on observation is known as qualitative data. In everyday terms, we would say that these are qualities. Qualitative data are qualities. So typically, this type of data is collected using your senses, and it would include things like color, texture, smell, and the list goes on. In the 1700s, we have a French chemist. Look at that, the name changed. He's no longer an alchemist, this is a chemist. French chemist Antoine Lavoisier changed the way that people approached chemistry. Lavoisier is a pretty interesting character. We will later in the school year look back at him and we might even watch a video. He was a wealthy Frenchman. He was a tax collector. He made a lot of money, and as a hobby, he had this chemistry lab, and it was very intense. He took an approach to chemistry like a tax collector would take with money. He was always tracking things like mass. He wanted to know all about the matter. Very interesting. The only issue was he was working right before the French Revolution, and in the French Revolution, he didn't come out so well. He wasn't very liked being wealthy and a tax collector and ended up losing his head. Lavoisier turned chemistry into a science of measurement. It was observations. Thanks to Lavoisier, it's a science of measurement. Measurements are more important than just observations. So Lavoisier very carefully measured each chemical involved in a chemical reaction. Very precise. He would measure everything before the reaction. He would measure everything after. We're going to do this same type of thing in this course. Based on measurements, we find data that is known as quantitative data. Or look at this, it is a quantity. A quantity is something that is counted or measured. This type of data will use numbers to record measurements. So the difference between qualitative data, which was maybe using senses, and quantitative data using numbers, could be illustrated by maybe the weather. Let's say you go outside today, and I haven't been outside today since the sun came up. Let's say yesterday. Yesterday it was really hot. It was about 85, pushing 90 degrees. Two ways to approach it. If I approached it using qualitative data, I would say it's hot outside, or it's really hot outside, or maybe some other creative way to express how hot it is. If I were to pull up a weather app and say it is 88 degrees, that is a quantitative number. If I measure it using numbers, it is quantitative. A related example, qualitative data. You could say it's really humid outside. On the quantitative side of that, we can measure humidity. relative humidity expresses how humid it is as a number between 1 and 100. So now we're going to look at types of measurements that are commonly made in our class. Mass. This is our first one. Mass is a measure of how much matter something has. In simple terms, mass is a measure of how much stuff is in an object. I'm going to put stuff in quotation marks because it's not exactly a scientific term. How much stuff is there? Is this a small object with a small amount of mass, or is it a very large object that probably has a large amount of mass? So we measure the amount of mass in an object with a unit called the gram. Symbol lowercase g. This is a metric measurement, and as you'll see throughout the next few units, we use metric measurements exclusively in this class. There's really no room for the US system in science. I don't like converting things from ounces to pounds, cups to pints, or whatever it is. It's too confusing. The metric system is all based on multiples of 10. So we use the gram. Since mass is the amount of matter that an object contains, the mass of an object is the same. It's going to be the same on the surface of the Earth. It's going to be the same standing on the moon if you were on board the International Space Station, or even if you were standing on a planet the size of Jupiter. So here's a quick look at some numbers. The mass of my body is very approximately 80 kilograms. So on the surface of the Earth, here I am, 80 kilograms. That's the amount of mass in my body. It's not really a weight, and we'll talk about how that's different in a minute. This is the mass of my object. How much stuff is there? How much water, how much muscle, how much fat, how much bone, how much brain tissue, digestive stuff, all of that. All of that plays into this number of how much stuff that my body contains. If I were on the moon, my weight is going to be different, and we've seen videos, but my mass is still 80 kilograms. If I were on board the International Space Station, if you see the astronauts there, they tend to just float around. My mass on the ISS would be 80 kilograms. If I were standing on Jupiter, I would have difficulty standing because the gravity is much stronger. However, my mass, or the amount of matter in my body on Jupiter, 80 kilograms. Probably the only difference, if I were able to stand on a planet the size of Jupiter, would be that I would feel much shorter very quickly. An important distinction here. This next idea is weight. And weight is different from mass. Weight is a measure of the force of gravity acting on an object's mass. The mass of an object does not change. We already talked about this one. My mass is not going to change. Your body has the same mass on the Earth and the moon. So let's remember my mass on the Earth, 80 kilograms, and my mass on the moon, 80 kilograms. but my weights are going to be different. The mass is remaining constant. It will not change. The force of gravity is going to vary. And here's how it's related. Your weight is 1/6 as great on the moon because the gravity on the moon is 1/6 as great as the Earth's. So a quick example of this, if my weight on the Earth, and remembering that kilograms is a measurement of mass, not weight, I'm going to give you some numbers here. So, weight. My weight is very approximately 180 pounds on Earth. On the moon, it would be 1/6 of this. So 180 times 1/6, or in other words, 180 divided by 6. So on the moon, my weight is going to be 30 pounds. Now it's going to be a little bit different. Remember, I haven't lost any of my mass. I'm still the same size and shape and all of that. It's just less gravity means I weigh less. The next concept is volume. Volume is a measure of how much physical space that matter occupies. So standard unit for volume is the liter. The liter is volume. And to put this into context, I guess, 1 liter is 2 regular water bottles. The plastic kind that you buy in bulk at the grocery store, or the water bottles that you get in the cafeteria, those are 1/2 liter. So 2 of those is a liter. In chemistry, it's more common for us to use milliliters, abbreviated lowercase m, capital L. So 1 liter equals 1,000 milliliters. Here it is. A typical plastic water bottle has a volume of 0.5 liters, which is the same as saying it is 500 milliliters. So we've talked about mass, talked about weight, talked about volume. Density is the relationship between the amount of mass an object has and how much volume the object has. So density is a measure of how much mass is contained in a given volume. In chemistry, we typically get densities in units of grams per milliliter. Grams per milliliter. And if we just pay careful attention to the units, it will even tell us how we can calculate density. Density is a useful measurement for identifying a substance, and we calculate it by dividing the mass of an object by its volume. I'm going to go ahead and write the formula here. D is density, M is mass, V is volume. Density is mass divided by volume. Here's some examples of how density could be used. Example 1, the U.S. Treasury changed the chemical composition of a penny in 1982. Prior to 1982, a penny was about 95% copper. Because the size and shape did not change, all pennies will have the same volume. So if you look at a penny and you were to, let's say you measure the diameter of a penny, it's going to be the same for one penny as the next penny. No matter what the year is, you could find a penny from 1960, its diameter is the same as the one from 2020. If you measure the depth, it would be the same no matter what year the penny was. Volume of a cylinder, that's the area of the circle times the thickness of the penny. They're all going to have the same volume. However, a penny with a greater mass has a greater density. So it turns out the pennies that were minted before 1982, being pure copper, are a little bit more dense than the pennies minted after 1982, which are mostly zinc. There is a lab associated with this one, and we will have to play this one by ear, see if they will allow us to do labs this year. Example 2, let's imagine that I want to measure the density of a marble. Okay, so I need to know two things, right? So density equals mass divided by volume. I have to know the mass and I have to know the volume. The mass of a marble is really pretty easy. We just take the marble and we place it on a balance, which is really just a technical term for this is like a scale. So the balances in our lab, they're pretty small and they can only hold about 200 grams, which is not a lot of weight, not a lot of mass. But it works just the same as a bathroom scale. So we put the marble on this balance and it will give us a number in grams. That part is relatively simple. The second part really is a little harder. Measuring the volume of a sphere could be difficult. So we could take out a ruler and we could do our best to measure the diameter, and then we could use a ruler, we could use a mathematical formula. If you know the mathematical formula for the volume of a sphere. On the other hand, it's much easier just to measure it. And here is the method for measuring the volume of oddly shaped objects. We want to measure the rise in water level in a graduated cylinder to measure the volume. So we have our two measurements now. Dividing the mass measurement by the volume measurement will tell us the density. Here's what we're looking at with the graduated cylinder. So the graduated cylinder is this very tall, skinny glass jar type thing. And it has markings that go all the way up that measure in terms of usually milliliters. And so what you would do is you find the original water level. And so let's say this is 1, 2, 3, 4, 5. That's the 5 millimeter marking. And then I take my marble and I put it in here. And if you were just to put it in here like this, it looks like it's 2 milliliters, but it's actually different. So it's a sphere, not a cylinder. And so maybe it goes up to here. Let's say it's 6.5 milliliters. Now the volume of the marble is not 6.5. It is 6.5 minus 5. So if I took 6.5 minus 5, and I find that my marble has a volume of 1.5 milliliters. This is a useful tool in chemistry and in some physics, so we will need to come back to this at some point and use it later in the school year. That's it for the third video. Thank you for watching. I will post the next one soon.